In this short video, we'll be looking at an introduction to groups. So there are 4 properties that must be met for a set of elements involved in a binary operation to be considered a group. Let's look a little more closely at that sentence. So set of elements is what type of numbers we're interested in. So even numbers, real numbers, complex numbers, etc. And by operation, typically we mean addition, subtraction, division, etc. But you also might have an operation which is multiply the first element by 7 and then add the second element or something similar. So the 4 properties of a group are closure, associativity, identity, and inverse. Now right from the start, it's good to note that identity and inverse are very closely related. So typically you'll need to find or to know the identity element in order to find the inverse. Closure and associativity are found quite independently. So what do these words mean? Closure. An operation is closed if the result of that operation is an element of the same set as the inputs. So if the input set is even numbers, then the output of the operation must also be an even number. Associativity. If an operation is associative, then the order in which the operations are performed does not affect the answer. So specifically, A operation B operation C equals A operation B operation C. So for example, if the operation is defined as A operation B equals A plus B, so just simple addition, then A plus B plus C equals A plus B plus C. Identity. So for all elements of a set, the identity element, which is normally indicated with the letter U, leaves all elements unchanged when the operation has been applied. So for addition of real numbers, the identity element U is equal to 0. Because if we add 0 to any real number, we get that same real number. For multiplication of real numbers, U, the identity element, is equal to 1, because any real number that we multiply by 1 will give us that same real number. And inverse, for each element of a set, there is a unique element, inverse of A, such that A operation inverse of A or inverse of A operation A, in either order, will give us the identity element U. So for real numbers under addition, the inverse of A is equal to negative A. So for example, 3 plus negative 3 equals 0, where 0 is the identity element for addition. So you can see we need to know what the identity element is in order to know or to find the inverse. For real numbers under multiplication, the inverse of A is 1 over A. So for example, 2 multiplied by a half is equal to 1, where 1 is the identity element for multiplication. So let's look at a familiar example. Question might be, show that the set of positive integers forms a group under addition. So we have our set, which is positive integers, and we have our operation, which is addition. Or show that set S, which is positive integers, forms a group under the operation A operation B equals A plus B. Those two sentences are saying the same thing. So first, closure. The question you're asking yourself is, when I perform addition on any pair of positive integers, is the result a positive integer? The answer is yes. Now, you don't necessarily need to prove this to be the case. You just give 1 or 2 examples. But bear in mind that to disprove closure, you only need to require to find a single counter instance or counter example, and that will show that closure isn't met. Associativity. The question is, when I perform the operation, addition, multiple times, does it matter which of the additions is completed first? And specifically, does A plus B plus C equal A plus B plus C? And the answer to that question is yes. Again, you don't need to prove it, but 1 or 2 examples is sufficient. So 1 plus 2 plus 3 is equal to 1 plus 2 plus 3. At this point, it's important to note, do not get this confused with commutativity, which requires that A operation B equals B operation A. That's a different requirement, a different property. We'll have a little bit of a look at that later. So identity. The question is there an element which, when addition is applied, leaves every element unchanged? And the answer to that question is yes, that the identity element for addition of real numbers is 0. And now to show this, we say A, any member of the set, plus U, the identity element, must equal A. So therefore U equals 0. The inverse, is there a unique inverse for every element such that A operation inverse of A equals inverse of A operation A equals the identity element. So when we do A operation inverse of A, we need to get the identity element. Now to show this for addition, we already found that the identity element is 0. So A plus the inverse of A equals 0. So the inverse of A is negative A for addition of real numbers. So this is obviously true. 1 plus negative 1 is 0. 2 plus negative 2 is 0, etc. So the conclusion we can draw there is that the set of positive integers forms a group under addition. Now let's look at a more complex example now. So show that the set of real numbers forms a group under the operation A operation B equals A plus B minus 1. So again, we've got our set, which is real numbers, and our operation is given there. So closure. For all real numbers, A plus B minus 1 will give a solution which is also a real number. So we can't possibly get a complex number or an imaginary number when we add two real numbers and subtract 1. So closure is met, therefore the operation is closed. Associativity. Show that A operation B operation C equals A operation B operation C. This is a little bit more complicated. So let's start with the left-hand side. So A operation B operation C looks like this. So A operation B is in brackets, and then we're going to perform the operation on C. So the first term plus the second term subtract 1, and we simplify that, we get A plus B plus C minus 2. The right hand side, we get A operation B operation C, so we're going to do the B operation C first. So it's A operation, and in brackets you can see we perform the operation on B and C, and then first term, second term plus second term minus 1 gives us A plus B plus C minus 2. Left hand side equals right hand side, therefore the operation is associative for real numbers. Identity. Okay, so we have to find the identity element such that A operation identity element equals A, essentially. So when we perform the operation on any number and the identity element, the result must be the original number. So A operation U looks like this, A plus U minus 1, and that must equal A. So our starting point is A plus U minus 1 must equal A. We rearrange that to end up with U equals 1. So we found our identity element for this operation. Similarly, we could do U operation A, and we get the same result. So the identity element is equal to 1. Let's check our original operation. So let's let A equal 4. We could pick any real number we wanted. We could pick a surd, we could pick a fraction or a decimal, but we'll just pick a positive integer to keep it simple. So let A equal 4. A operation U. So we said that A is equal to 4. We've just found the identity element is U is equal to 1. So 4 operation 1 is 4 plus 1 minus 1, which equals 4. So when we perform the operation on any real number and the identity element, we get back to that original real number. Now, finding the inverse. So we've just found the identity element, and now we need to find an inverse such that A operation inverse of A equals U, which in this case is equal to 1, which we've just found. So it looks like this. A plus inverse of A minus 1 must equal 1. And then when we simplify that, we get to the point where the inverse of A equals 2 minus A. So let's just check that with a real example. So let's let A equal negative 3. And in under this operation, the inverse of negative 3 is going to be 2 minus A, which is 2 minus negative 3, which is equal to 5. So the inverse of negative 3 under this operation is equal to 5. So now let's do A operation inverse of A, and what we're hoping is that we'll end up with U. We'll end up with the identity element. So A operation inverse of A is negative 3, which we chose as A, and operation 5, which is we found to be the inverse of A, which equals negative 3 plus 5 minus 1, which equals 1, which is the identity element. So that the inverse of any element under that operation is 2 minus A. So the conclusion, the set of real numbers forms a group under the operation A operation B equals A plus B minus 1. Now there's another step to this, which is to investigate whether the group is an abelian group, and for a group to be an abelian group, it must meet the 4 criteria that we've just discussed, but the operation must also be commutative. That is, A operation B must equal B operation A. So to summarize all of that information, there are 4 properties that must be met. First one is closure. So is the output of the operation a member of the set of original inputs? Secondly, associativity. So does A operation B operation C equal A operation B operation C? Identity. So we find the identity element U such that A operation U equals A. So when calculating the identity, you should start with that statement and work from there. And then having found the identity, we can find the inverse of A such that A operation inverse of A equals U. So that statement should be your starting point when finding the inverse.